Imagine starting with pure static, a screen full of random noise, and transforming it into a photorealistic image. It sounds like magic, but that's precisely what diffusion models allow us to do.
It feels counterintuitive. We usually try to remove noise. How does starting with noise help us generate something specific and clear? What's the trick here?
Today, we're focusing on the foundational paper for denoising diffusion probabilistic models, or DDPMs. This work really established how to train these powerful generative models effectively.
We touched on diffusion models generally in #TCM123001, talking about how they evolve latent space. Is this paper the basis for that evolution?
Exactly. This paper showed how DDPMs could achieve high-quality image synthesis results that rivaled and in some cases surpassed other state-of-the-art generative models at the time.
So this is the paper that really brought diffusion models into the mainstream for image generation?
It was a big step. Their approach was inspired by considerations from non-equilibrium thermodynamics. Think of a droplet of ink diffusing in water. It's a natural process moving towards disorder.
So they're modeling a process that naturally goes from order to disorder, but then how do they get it to go the other way?
They found a novel connection to Langevin dynamics. This is a concept from physics, describing how particles move randomly but with a drift. It gives us a mathematical way to reverse that natural diffusion.
So we're mimicking a physical process that disperses things and then trying to run it backward to concentrate information.
That's the core idea. The results spoke for themselves, achieving a state-of-the-art FID score of 3.17 on CIFAR-10. FID, or Fréchet inception distance, is a key metric for image quality.
That's an impressive number for the time. It shows these models weren't just a theoretical curiosity, but genuinely competitive.
Exactly. They achieved sample quality similar to progressive GAN on 256 by 256 LSUN. This indicated diffusion models could generate complex, high-resolution images, a significant milestone.
So they showed that the physical inspiration and the mathematical framework translated into real-world performance.
Now that we've seen the what and the why, let's really dive into the how. We'll break down the two key phases of a DDPM, adding noise and then learning to reverse it. The process starts with a clean image, x0. We then define a Markov chain of diffusion steps that slowly adds Gaussian noise to it. Think of adding salt to a clear glass of water, one grain at a time.
So each step xt is just xt minus 1 with a little more noise added? Eventually it just becomes pure noise, like a completely cloudy glass?
Precisely. The blog explains that the data sample x0 gradually loses its distinguishable features until xt is essentially just an isotropic Gaussian distribution. It's a controlled degradation.
That part makes sense. It's just a forward process of adding noise. The real magic has to be in reversing it, right?
Absolutely. The goal is the reverse diffusion process, to sample from xt, pure noise, and gradually denoise it back to x0. We need to learn a model p theta to approximate these conditional probabilities for each step.
So the model needs to learn how to undo each tiny bit of noise we added. How does it know what noise was added at each specific step?
This is where the connection with stochastic gradient Langevin dynamics comes in. It provides a theoretical grounding for why estimating the score function, the gradient of the log probability density, can guide us backward.
So the model isn't just blindly guessing, it's using an estimated direction to clean up the noise, similar to how an optimization algorithm uses gradients?
It is. The key insight from Ho et al. Is in the parameterization of LT for training loss. Rather than directly predict the mean of the reverse step, which is complex, they predict the noise itself.
Wait, you're saying instead of predicting the clean image or the next denoised step, the model predicts the noise that was added? Why predict noise?
It's brilliant. At training time, we know exactly what noise, epsilon of t, was added to get x of t from x naught. So we train a neural network to predict epsilon of t from the input x of t for any given time step t.
So during training, it's a supervised learning task. The network sees a noisy image and tries to guess the noise. Then during generation, it predicts noise and subtracts it to denoise.
That's exactly right. Empirically, Ho et al. Found that training works better with a simplified objective that ignores the weighting term. The final loss is just the mean squared error between the predicted and actual noise.
A simple mean squared error loss to predict noise. It seems almost too straightforward for such powerful results.
It is elegant. The predict epsilon t strategy implicitly guides the model toward the correct mean and variance for the reverse steps, making the entire process stable and effective. It's not just predicting random noise, but the specific noise that degrades the image.
So the simplicity hides a deep connection between denoising and probability density estimation. It clicks.
DDPMs clearly showed the potential, but they had a major bottleneck. Working in pixel space was computationally expensive. This limited their ability to generate truly high-resolution images efficiently. Now we turn to the solution.
So DDPMs are powerful, but you mentioned a bottleneck. What was the main issue when trying to scale them up to really high-resolution images, like 1024 by 1024?
The core problem is that these models typically operate directly in pixel space. Imagine the computational cost of adding and removing noise for millions of pixels across hundreds of steps.
This pixel-level operation means that optimization of powerful DMs often consumes hundreds of GPU days. And inference, generating a single image, can also be painfully slow due to sequential evaluations.
Hundreds of GPU days for training? That's not just expensive, it's a huge barrier for anyone without massive computational resources.
Exactly. The innovation of latent diffusion models is to apply them in the latent space of powerful pre-trained autoencoders. Instead of diffusing pixels, we diffuse a compressed representation of the image.
So we're not adding noise to the actual image, but to a kind of abstract summary of it, like sketching instead of painting every detail?
A great analogy. A pre-trained autoencoder learns to compress images into a lower dimensional latent space and then reconstruct them. Latent diffusion then performs the denoising within this compact, perceptually rich space.
Does that compromise the quality? It seems like you'd lose too much information by compressing it first.
That's the critical balance. The authors state this approach allows for the first time to reach a near-optimal point between complexity reduction and detail preservation, which was key to its success.
So the autoencoder creates a bottleneck, forcing the model to learn the most important features, and then a diffusion process operates on those features.
Precisely. They further enhance this by introducing cross-attention layers into the model architecture. This allows for conditioning the generation process with text prompts or other inputs.
So this is how you can tell a diffusion model to generate a cat wearing a spacesuit. The text prompt guides the denoising in the latent space.
Exactly. This dual approach of latent space diffusion and cross-attention enables greatly boosting visual fidelity while also making the process much more efficient and controllable.
It's amazing how combining these ideas solves the scalability problem without sacrificing quality.
The outcome is clear. LDMs achieve new state-of-the-art results across various tasks, significantly reducing computational requirements compared to pixel-based diffusion models. This opened the door for wider adoption.
So if you need to generate high-resolution images efficiently, especially with text or other conditioning, latent diffusion is the approach to reach for.
I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.